Hello there, wherever in the world you might be right now. I'm really glad you've joined me. Whether you're settling into bed, winding down after a long day, or simply letting your mind drift into something a little stranger, tonight, we're going on a journey into one of the most puzzling mysteries humanity has ever tried to understand, something so deeply woven into our lives that we hardly notice it. And yet, it might not even be real. Does time actually exist? It's a strange question, isn't it? Because even as you're hearing these words, you're experiencing time. But the deeper we look through physics, philosophy, or even our own memories, the more slippery it becomes. You can't see it, you can't hold it, you can't measure it like weight or color, yet it defines everything: our past, our future, our very sense of now. Before we begin, take a moment to drop a comment below. Let me know where in the world you're listening from, and what time it is for you right now. There's something beautiful about seeing the whole world gently link through this one moment. Alright, let's begin. Let's begin our journey in the ancient world, where humans first tried to catch time and pin it down. Picture yourself in ancient Egypt, where the morning sun casts long shadows across the desert sand. Someone, perhaps a priest or an astronomer, noticed something remarkable. Those shadows moved in a predictable pattern, creeping across the ground like a slow, celestial finger, pointing to different moments of the day. And so the sundial was born, humanity's first attempt to make time visible. It wasn't just a tool for telling time, it was a declaration that time could be measured, divided, and understood. The Egyptians were essentially saying, we can capture this invisible force and make it serve us. But here's what's fascinating. They weren't measuring time itself. They were measuring the Earth's rotation, the sun's apparent movement across the sky, the angle of shadows on stone. They were measuring change, motion, the relationship between celestial objects. Was that time? Or was time something else entirely? Something that allowed these changes to unfold? The ancient Greeks wrestled with this question too. Aristotle suggested that time was simply the measure of change. Without change, he argued, there would be no time. It's a beautiful idea, isn't it? Time is the rhythm that allows the universe to dance from one moment to the next. But then there was Plato, who wondered if time might be something more fundamental, a backdrop against which all change occurs, like a vast invisible stage where the drama of existence unfolds. Two competing ideas that still echo through physics today. Is time something that emerges from change? Or is change something that happens within time? The Romans, practical as always, divided their days into hours, their months into calendars, their years into history. They built water clocks that dripped steadily through the night, mechanical devices that seemed to prove time's relentless, measurable flow. Each drop of water was like a tiny heartbeat of the universe, marking another moment gone forever. Yet even as these ancient civilizations built increasingly sophisticated ways to measure time, they couldn't escape the fundamental mystery. They could track the sun's movement, count the moon's phases, mark the changing seasons, but they couldn't actually touch time itself. They were like people trying to catch shadows, creating increasingly elaborate nets to hold something that might not even be there. The medieval monasteries carried this tradition forward, dividing their days into periods of prayer and work, their bells marking the hours with mathematical precision. Time became something to be disciplined, organized, controlled. The universe was seen as a great clockwork mechanism, with God as the ultimate clockmaker. But even in their certainty, these ancient timekeepers were grappling with something profound. They were assuming that time was universal, that their local experience of morning and evening, of seasons and years, reflected some deeper truth about the nature of reality itself. They couldn't have imagined that centuries later, a patent clerk in Switzerland would discover that their assumptions about time's universality were beautifully completely wrong. Albert Einstein had a problem, not with mathematics or physics. He was brilliant at both. His problem was with something far more fundamental. He couldn't accept that time was what everyone thought it was. Picture Einstein in 1905 working in the Swiss patent office, reviewing applications for electrical devices, while his mind wandered to the deepest questions about space and time. He was bothered by something that seemed almost trivial. If you're on a train moving away from a clock tower, and you look back at the clock, What time does it show? This wasn't just idle curiosity. Einstein had realized that light travels at a finite speed, about 300,000 kilometers per second. This meant that when you look at that clock tower, you're not seeing it now, you're seeing it as it was a tiny fraction of a second ago. The light from the clock face had to travel through space to reach your eyes. But here's where it gets strange. Einstein realized that there's no such thing as now, that everyone can agree on. If you're on that train, moving away from the clock, the light has to travel a bit farther to reach you. From your perspective, the clock appears to be running slightly slower, not because anything is wrong with the clock, but because simultaneity, the idea that events can happen at the same time, is relative. This was revolutionary. For centuries, people had assumed that time was like a great river flowing at the same rate everywhere. In the universe, Einstein showed that time is more like a stretchy fabric that can be pulled and twisted, depending on how fast you're moving and where you are in the universe. Imagine two friends, Sarah and Maya. Sarah stays on Earth while Maya travels to a distant star at nearly the speed of light. When Maya returns, she'll find that less time has passed for her than for Sarah. They started their journey at the same now, but they end up in different nows. Which one experienced the real time? Einstein's answer was both profound and unsettling. They both did. Time isn't a universal constant. It's a personal experience. Your time belongs to you, shaped by your motion through space and your position in gravitational fields. The universe doesn't have a master clock keeping everything synchronized. Instead, it has billions of personal clocks, each ticking at its own rate. This leads to something even more mind-bending: the relativity of simultaneity. Events that appear simultaneous to you might occur at different times for someone else. The very concept of now becomes meaningless on a cosmic scale. There's no universal present moment, no slice of time that cuts through the entire universe. Einstein called this the block universe, the idea that past, present, and future all exist equally. From this perspective, time doesn't flow like a river. Instead, all moments exist simultaneously in a four-dimensional space-time. Your birth, your childhood, this very moment, and your future, all equally real, all equally present in the mathematical structure of reality. But if that's true, then what we experience as the passage of time might be an illusion. The feeling that time flows, that the present moment is special, that the past is gone and the future is yet to come. All of this might be a trick of consciousness, a limitation of our perspective rather than a fundamental feature of reality. When you count 1 Mississippi, 2 Mississippi, you're participating in one of humanity's most ambitious projects, the attempt to standardize time itself. But what exactly are you counting? What is a second really? For most of human history, a second was defined as 1/86/400th of a day, one tick of the cosmic clock as Earth spins on its axis. It seemed perfectly reasonable. The sun rises and sets, the Earth turns, and we divide this natural rhythm into hours, minutes, and seconds. Simple, elegant, and completely wrong. The problem, scientists discovered, is that Earth is a terrible timekeeper. Our planet's rotation is gradually slowing down like a spinning top, losing energy. Some days are longer than others, influenced by weather patterns, earthquakes, and the gravitational pull of the moon. If you defined a second based on Earth's rotation, then the length of a second would be constantly changing. So in 1967, scientists made a remarkable decision. They stopped looking to the heavens for the definition of time and started looking into the heart of atoms. They chose cesium-33, a particular isotope of cesium, and focused on something extraordinary: the natural vibration of electrons within cesium atoms. Here's where it gets beautifully strange. Cesium atoms vibrate at an incredibly precise frequency, exactly 9,192 tons and 31,070 times per second. It's like having the universe's most perfect metronome, a rhythm so steady that it makes the most precise mechanical clocks look like children's toys. But think about what this means. When you experience a second, when you feel that familiar tick of time passing, you're experiencing the collective vibration of billions of cesium atoms. The second isn't a piece of time that exists out there in the universe. It's a human construct, a unit of measurement we've imposed on the natural rhythms of matter itself. This raises a profound question. Are we measuring time, or are we creating it? When atomic clocks tick, are they discovering the fundamental rhythm of reality? Or are they manufacturing a human concept of temporal order? The precision is almost incomprehensible. The best atomic clocks are so accurate that they would lose less than a second over the entire age of the universe, about 13.8 billion years. They're sensitive enough to detect the tiny differences in time flow caused by gravity. If you move an atomic clock just a few centimeters higher, it will run slightly faster because gravity's effect is infinitesimally weaker. This precision has practical consequences that touch your daily life. GPS satellites orbiting Earth carry atomic clocks, and they have to account for both the effects of their motion, special relativity, and their position in Earth's gravitational field, general relativity. Without these relativistic corrections, GPS would be off by several kilometers. Your phone's ability to tell you where you are depends on Einstein's insights about the nature of time. But the deeper question remains, what are these clocks actually measuring? They're counting vibrations, marking rhythms, dividing change into standardized units. But is that time itself, or is it just our way of organizing our experience of duration? Perhaps a second is like a word, a useful symbol that points to something real, but isn't the thing itself. When you say love, the word isn't love itself, but it helps you communicate something profound. When an atomic clock ticks off a second, it's not capturing time itself, but it's marking something fundamental about the way reality unfolds. Right now, as you're listening to these words, you're experiencing something that might not exist. The present moment. You feel it, don't you? This sense of now. This feeling that you're balanced on the knife's edge between past and future. But according to physics, this feeling might be the most beautiful illusion your mind creates. Think about what now means to you. It's not just this instant, it's a kind of window, a brief span of time that feels present and immediate. When you listen to music, you don't hear individual notes in isolation. You hear melodies that unfold over several seconds. When someone speaks to you, you don't process each syllable separately. You hear words and sentences that take time to complete. Your brain constructs the present moment from a stream of sensory information that arrives at slightly different times. Light from the lamp across the room reaches your eyes almost instantaneously, but sound from the same location takes a few milliseconds longer. Your brain somehow weaves these different streams of information together into a single coherent experience of now. But here's the puzzle. Physics suggests that there's no objective present moment. Einstein showed us that simultaneity is relative. Events that are simultaneous for you might not be simultaneous for someone else. There's no universal now that cuts through the entire universe like a cosmic knife. From the perspective of space-time, all moments are equally real. Your birth, your childhood, this moment, and your future, they all exist as fixed points in the four-dimensional structure of reality. The mathematical description of the universe doesn't include a moving spotlight of now that illuminates one moment at a time. So why do you experience the present so vividly? Why does it feel like time flows, like moments pass from future to present to past? Some scientists think this feeling emerges from the way your brain processes information. You remember the past, you anticipate the future, but you can only experience the present. The present moment might be the boundary between memory and anticipation, a psychological artifact rather than a fundamental feature of reality. Others suggest that the present moment might be related to consciousness itself. Perhaps consciousness is what creates the experience of now by selecting which slice of spacetime to pay attention to. In this view, the present moment isn't an illusion, it's the fundamental interface between mind and reality. There's also the quantum perspective to consider. In quantum mechanics, the act of observation seems to play a special role in determining reality. Some interpretations suggest that the present moment might be where quantum possibilities collapse into definite outcomes. The now might be the boundary where the fuzzy, probabilistic quantum world crystallizes into the definite, classical world we experience. But even if the present moment is an illusion, it's a remarkably persistent and convincing one. You can't help but experience it right now, as you listen to these words. You're creating a sense of temporal order, a feeling that some things are immediate and present while others are remembered or anticipated. Perhaps the question isn't whether the present moment exists, but why it feels so real. What is it about consciousness about the way your brain processes information, that creates this vivid sense of temporal flow. The present moment might be like a rainbow, not a thing in itself, but a beautiful pattern that emerges from the interaction between light, water, and observation. Here's something curious. You can scramble an egg, but you can't unscramble it. You can watch a sandcastle crumble, but you'll never see sand spontaneously organize itself into a castle. Time, it seems, has a direction, an arrow that only points one way. This might seem obvious, but it's actually one of the deepest mysteries in physics. The fundamental laws of physics, the equations that describe how particles interact, how forces work, how energy flows, are almost all reversible. If you filmed these interactions and played the film backward, the reversed version would look just as physically plausible as the original. So why does time seem to have a direction? Why do we remember the past, but not the future? Why do things tend to break down, rather than spontaneously organize themselves? The answer involves something called entropy, a measure of disorder or randomness in a system. The second law of thermodynamics tells us that entropy in a closed system always increases over time. This sounds technical, but it's actually describing something you experience every day. The tendency of organized things to become disorganized. Your room doesn't clean itself, it gets messy over time. Your coffee doesn't stay hot forever, it cools down to match the temperature of the room. Your body doesn't maintain itself automatically. It requires constant energy input to stay organized and alive. In each case, you're witnessing the increase of entropy, the universe's tendency to spread energy around more evenly. But here's the beautiful part. This increase in entropy might be what creates the arrow of time. The direction from past to future might be the direction in which entropy increases. Time doesn't flow like a river. Instead, the universe evolves from states of lower entropy to states of higher entropy, and we interpret this evolution as the passage of time. This creates a fascinating picture of the universe. At the beginning, in the moments after the Big Bang, the universe was in an incredibly low entropy state. Everything was squeezed together, highly organized, full of potential. Since then, the universe has been relaxing, spreading out, increasing in entropy. Stars formed and will eventually burn out. Galaxies are moving apart, and the universe is gradually cooling down. In this view, time's arrow isn't fundamental, it's statistical. It emerges from the fact that there are many more disorganized states than organized ones. If you drop a glass, it's overwhelmingly likely to shatter into many pieces rather than bounce back intact. Not because of any law that prohibits bouncing, but because there are so many more ways for a glass to be broken than to be whole. Your memory works the same way. You remember the past because your brain creates records of events, increasing the overall entropy of the universe. You can't remember the future because that would require your brain to spontaneously organize information in a way that decreases entropy. But this raises a puzzling question. Why did the universe start in such a low entropy state? Why wasn't it random and disorganized from the very beginning? This is one of the deepest unsolved problems in physics. Some scientists think it might be related to the nature of the Big Bang itself. Others suggest it might involve multiple universes or exotic physics we don't yet understand. Perhaps the arrow of time is like a river after all. Not because time flows, but because the universe is like a landscape and entropy is like gravity, pulling everything downhill from organization to randomness. The river doesn't flow because of time. Time emerges because of the river. Have you ever noticed how time seems to play tricks on you? How a watched pot never boils, but an engaging conversation can make hours feel like minutes. How childhood summers stretched on forever, but adult years seem to flash by in an instant. This isn't just your imagination. Time really does behave differently depending on your state of mind. Your brain doesn't have a single clock that measures time objectively. Instead, it has multiple timing systems, each influenced by different factors. Your attention, your emotions, your age, your arousal level, even your body temperature. These systems work together to create your personal experience of time's passage, but they don't always agree with each other. When you're bored, your brain's timing circuits seem to slow down. You become acutely aware of time passing, checking clocks repeatedly, feeling trapped in an endless moment. But when you're deeply absorbed in something you love, reading a good book, having a meaningful conversation, losing yourself in music, these same timing circuits seem to speed up. Hours can pass without you noticing. This isn't just a quirk of consciousness. It's a fundamental feature of how your brain processes temporal information. Your perception of time is constructed from multiple sources: the rhythms of your neural activity, the amount of information you're processing, the emotional significance of what you're experiencing, and your expectations about how long things should take. Children experience time differently than adults, and this difference is measurable. To a 5-year-old, a year represents 20% of their entire lifetime. To a 50-year-old, that same year is only 2% of their lived experience. This proportional theory of time perception helps explain why childhood summers felt endless, while adult years seem to accelerate. But there's more to it than simple mathematics. Children's brains are constantly processing new information, forming new memories, building new neural connections. Each day brings novel experiences that require attention and processing. Adults, by contrast, often fall into familiar routines, where days blend together into forgettable patterns. Your emotional state also dramatically affects your perception of time. When you're anxious or afraid, time seems to slow down. This isn't just a feeling, it's a survival mechanism. In dangerous situations, your brain processes information more quickly, creating more detailed memories and giving you more time to respond. The car accident that happens in slow motion, the fall that seems to last forever, these are examples of your brain's emergency time dilation system. Depression can distort time perception in the opposite direction. When you're depressed, the future seems both distant and threatening. The present feels stuck and unchanging, and the past becomes a source of rumination. Time loses its forward momentum and becomes something to be endured rather than experienced. Even your body temperature affects how you experience time. When you have a fever, time often feels distorted. Minutes can feel like hours, and hours can disappear without notice. This suggests that your perception of time is intimately connected to the physical processes of your brain and body. Culture also shapes how you think about time. Some cultures view time as linear, a straight line from past to future. Others see it as cyclical, with patterns that repeat across generations. Still others experience time as more fluid, with past and future interconnected in complex ways. Perhaps the most beautiful aspect of temporal perception is its subjectivity. Your experience of time is uniquely yours, shaped by your memories, your attention, your emotions, and your physical state. When you share a moment with someone, watching a sunset, listening to music, having a deep conversation, you're not just sharing space, you're synchronizing your subjective experiences of his time. This suggests that time might be less like a river and more like a symphony, something that exists in the interaction between consciousness and reality. Your brain doesn't just measure time, it creates time, moment by moment, experience by experience. The question isn't whether time exists, but how many different kinds of time there are, and how they weave together to create the rich tapestry of temporal experience. Imagine, if you will, that you could step outside our universe and look back at it like a snow globe on a shelf. What would you see? And more intriguingly, what would be sitting on the shelves beside it? This is where our journey begins. In the vast library of possible universes, each potentially keeping time in its own peculiar way. You see, if the multiverse theories are correct, our universe with its steady tick-tock of seconds and centuries might be just one timekeeper among infinite others, each marching to its own cosmic drummer. In some of these parallel worlds, time might flow like thick honey, where what we call a heartbeat stretches across what we'd recognize as years. Picture beings there living entire lifetimes in what feels to them like a normal pace, while, from our perspective, they'd appear frozen like statues. Their thoughts would unfold like slow-motion poetry, their conversations spanning decades of our time, yet feeling perfectly natural to them. Then there are universes where time races like a hummingbird's wings. Entire civilizations might rise and fall in what we'd experience as a single breath. Their scientists might puzzle over our universe, wondering how anything could move so impossibly slow and still function. To them, we'd be the frozen ones, suspended in amber-like stillness. But here's where it gets deliciously strange. Some universes might have multiple streams of time, flowing in different directions simultaneously. Imagine a world where cause and effect dance together in ways that would make our philosophers dizzy. A universe where you could have tea with your future self, not because of time travel, but because future and past exist side by side like rooms in the same house. The mathematics of quantum mechanics whispers about universes where time isn't a river flowing in one direction, but more like a vast ocean where past, present, and future are all equally real and accessible. In these realms, beings might experience all moments of their lives simultaneously: birth, childhood, old age, death. Not as a sequence, but as a single eternal now. Consider the universe where time moves in spirals rather than straight lines. Here, events don't just happen once, but echo and return, creating patterns of recurrence that would seem magical to us. Or perhaps a universe where time is granular, made of discrete moments, like frames in a cosmic film strip, with gaps of pure nothingness between each instant of existence. Some cosmologists suggest there might be universes where time doesn't exist at all. Realms of pure being where change and sequence are meaningless concepts. In these timeless domains, consciousness might exist in a state of perpetual present, experiencing all possibilities simultaneously, without the need for temporal progression. The most mind-bending possibility is that each universe might create its own time through the very act of existing. Time wouldn't be a stage upon which cosmic events play out, but rather the music that emerges from the dance of particles and forces. In this view, asking whether time exists becomes like asking whether a symphony exists, apart from the instruments playing it. What makes this more than just beautiful speculation is that our own universe shows us hints of time's flexibility. Near black holes, time stretches like taffy. At the quantum level, particles seem to ignore our neat timelines entirely. Perhaps we're getting glimpses of what time looks like from the perspective of the multiverse itself. Fluid, malleable, and far stranger than our everyday experience suggests. As we drift through these possibilities, we begin to see that the question isn't just whether time exists, but whether existence itself requires time. And that gentle mystery will follow us through every chapter of our journey tonight. Picture yourself floating in space, watching Earth spin slowly beneath you. You're moving fast, really fast, approaching the speed of light. Something extraordinary begins to happen. Time starts to behave strangely. Not just your perception of time, but time itself. This isn't science fiction, it's Einstein's special relativity, and it reveals something profound about the nature of time. The faster you move through space, the slower you move through time. It's as if the universe has a speed limit, and when you approach it, time itself begins to stretch and bend. Imagine you're traveling to a distant star at 99% the speed of light. The journey takes you 1 year from your perspective. You celebrate your birthday, watch movies, read books, live a full year of life. But when you return to Earth, you discover that 10 years have passed for everyone else. Your friends have aged a decade, while you've aged only 1 year. You've effectively traveled into the future. This isn't just theory, it's been measured with atomic clocks on airplanes, observed in the behavior of particles in accelerators, and it's essential for GPS satellites to work properly. Time dilation is real, and it tells us something startling. Time isn't the universal constant we thought it was, but it gets even stranger near black holes. Imagine approaching the event horizon of a massive black hole. As you fall toward it, time slows down relative to observers far away. To someone watching from a safe distance, you would appear to freeze at the event horizon, your image gradually fading as light becomes redshifted. But from your perspective, you would continue falling, experiencing time normally until things get very complicated indeed. This is gravitational time dilation, and it suggests that time is intimately connected to the fabric of space itself. Massive objects don't just bend space, they bend time. The stronger the gravitational field, the slower time moves. It's as if time is a river that flows at different speeds depending on the gravitational landscape it's flowing through. But here's the mind-bending part. You can never actually stop time completely. Even at the speed of light, time doesn't stop. It becomes undefined, meaningless. And at the event horizon of a black hole, time doesn't stop either. It becomes infinitely dilated relative to outside observers. This raises a profound question. If time can be stretched and compressed, if it flows at different rates in different places, what does it mean to ask whether time exists? Are we talking about your personal time, cosmic time, or some absolute time that transcends all reference frames? Perhaps the question isn't whether you can stop time, but whether time is something that can be stopped at all. Maybe time isn't a river that flows, but a dimension that can be navigated, stretched, and explored. Maybe asking whether time exists is like asking whether space exists. It's not a thing, so much as a framework, a stage upon which the drama of existence unfolds. Let's travel back to the beginning. Not just the beginning of our story, but the beginning of time itself. About 13.8 billion years ago, everything we know emerged from a singularity in an event we call the Big Bang. But here's something wonderful to consider. Time itself might have been born in that moment. Before the Big Bang, there was no before. It's not that time existed, and then the universe began. It's that time and space came into existence together, like two dancers entering the stage simultaneously. This is cosmic time, and it's been expanding ever since. Picture the universe as a balloon being inflated. Every point on the balloon's surface is moving away from every other point, not because they're moving through space, but because space itself is expanding. Similarly, galaxies aren't flying apart through pre-existing space. The space between them is growing, carrying them along like raisins in rising bread dough. This expansion affects time in subtle but profound ways. As the universe grows larger and cooler, the cosmic background radiation that fills all of space becomes redshifted, stretched to longer wavelengths. This redshift isn't just about light, it's about time itself. The universe is aging, and we can measure that aging by observing how light from distant galaxies is stretched by the expansion of space-time. When astronomers look at distant galaxies, they're seeing them as they were billions of years ago, when the universe was younger, denser, and hotter. The light from these galaxies has been traveling through expanding space for eons, and by the time it reaches us, it carries information about cosmic time itself. But here's where it gets beautifully complex. Different parts of the universe might experience time differently. If the expansion isn't perfectly uniform, if some regions are denser than others, if there are massive structures that warp space-time, then cosmic time might flow at slightly different rates in different places. The birth of stars adds another layer to this temporal tapestry. When a massive star forms, it creates a gravitational well that affects the flow of time around it. When that star eventually dies and becomes a neutron star or black hole, it creates even more extreme distortions in space-time. The universe isn't just expanding, it's constantly reshaping the very fabric of space and time. This raises fascinating questions about the nature of cosmic time. Is there a universal clock that measures the age of the universe, or does each region of space have its own relationship with time, its own rate of aging? When we say the universe is 13.8 billion years old, whose time are we using? Perhaps the most poetic aspect of cosmic time is that it connects us to the deepest history of existence. The atoms in your body were forged in the hearts of ancient stars, and the light you see from distant galaxies left its source when the universe was young. You're not just existing in time, you're participating in the grand temporal symphony that began with the Big Bang and continues to unfold across the cosmos. Welcome to the quantum realm, where time becomes as mysterious and uncertain as everything else. In the everyday world, time seems to flow smoothly from moment to moment, like a river flowing steadily toward the sea. But at the quantum level, time becomes fuzzy, uncertain, and deeply strange. Imagine trying to measure exactly when something happens at the quantum scale. You might think this would be straightforward, just look at your finest clock and note the precise moment. But Heisenberg's uncertainty principle tells us that the more precisely you try to measure the energy of a quantum system, the less precisely you can know when that measurement occurs. Energy and time are connected by fundamental uncertainty. This isn't just a limitation of our measuring instruments, it's a fundamental feature of reality itself. At the quantum level, events don't have precise timestamps. Instead, they exist in a fuzzy cloud of probability, where the timing of events becomes meaningful only when we zoom out to larger scales. Think of it like trying to photograph a hummingbird's wings. If you use a very fast shutter speed to capture the exact position of the wings, you lose information about their motion. If you use a slow shutter speed to capture the motion, you lose information about their precise position. At the quantum level, time and energy have a similar relationship. You can't pin down both with perfect precision. This creates a fascinating puzzle. If time is fuzzy at the quantum level, how does it become so definite and smooth at the macroscopic level? The answer involves something called decoherence, the process by which quantum systems lose their quantum properties and begin to behave classically. When quantum particles interact with their environment, they become entangled with countless other particles. This entanglement gradually destroys the quantum superposition that allows particles to exist in multiple states simultaneously. As decoherence progresses, the fuzzy, probabilistic nature of quantum time gives way to the definite, flowing time we experience in everyday life. But there's another mystery. Quantum mechanics seems to be fundamentally timeless. The Schrödinger equation, which describes how quantum systems evolve, doesn't actually require time to flow. It describes how the state of a system at one time is related to its state at another time, but it doesn't explain why we experience time as flowing from past to future. Some physicists think this suggests that time might be an emergent property, something that arises from the collective behavior of quantum systems rather than being fundamental to reality. Just as temperature emerges from the motion of countless atoms, time might emerge from the quantum interactions of countless particles. This leads to some mind-bending possibilities. If time is emergent, then at the deepest level of reality, there might be no time at all. The universe might be fundamentally timeless, with time arising only when quantum systems interact and decohere. Your experience of temporal flow might be a kind of collective illusion created by the quantum dance of particles in your brain. Here's something that might surprise you. The most fundamental laws of physics don't actually need time. They're written in a language that's essentially timeless, describing relationships between quantities without requiring time to flow from past to future. Take Newton's laws of motion, for instance. They tell us how objects move, but they don't distinguish between forward and backward in time. If you filmed a collision between two perfectly elastic balls and played the film backward, the reversed version would obey Newton's laws just as well as the original. The equations themselves are time reversible. Einstein's equations of general relativity are even more striking in their timelessness. They describe the curvature of space-time, the relationship between matter and geometry, but they don't require time to flow. Instead, they treat time as just another dimension, like the three dimensions of space. From this perspective, the universe is a static four-dimensional sculpture, and what we call time is just our particular way of moving through it. Even quantum mechanics, for all its strangeness, is fundamentally timeless. The Schrödinger equation describes how quantum states evolve, but it doesn't explain why we experience that evolution as a flow from past to future. It's like a mathematical recipe that relates different slices of reality, without requiring those slices to be experienced in any particular order. This creates a profound puzzle. If the fundamental laws of physics are timeless, where does our experience of time come from? Why do we remember the past, but not the future? Why do we experience cause and effect? Why does time seem to flow? Some physicists think the answer lies in the initial conditions of the universe. The Big Bang created a universe with very low entropy, a highly organized state that has been evolving toward higher entropy ever since. This increase in entropy might be what creates the arrow of time, the sense that time flows from past to future. But this raises another question. Why did the universe start with such low entropy? This is one of the deepest unsolved problems in physics. Some theories suggest it might be related to the nature of the Big Bang itself. Others propose the existence of multiple universes, or exotic physics we don't yet understand. The timeless nature of physical laws also suggests something profound about the nature of mathematical truth. Mathematics itself seems to be timeless. The theorem that the square root of 2 is irrational was true before humans discovered it, and it will remain true long after humans are gone. Perhaps the universe is fundamentally mathematical, and time is just the way conscious beings experience mathematical relationships. This leads to a beautiful paradox. The equations that describe time don't need time to be meaningful. They exist in a realm of pure mathematical relationships, timeless and eternal. Your experience of time might be like reading a book. The entire story exists simultaneously on the printed page, but you can only experience it one word at a time. Here's a curious question that touches the heart of time's mystery. Do particles remember their past? When an electron spins or a photon travels across the universe, is it carrying information about where it's been and what it's experienced? The answer depends on what we mean by memory. In the everyday sense, memory involves storing information about past events and retrieving it later. Your brain creates neural patterns that encode experiences, allowing you to remember your childhood, what you had for breakfast, or where you left your keys. But particles seem to have a different kind of memory, one that's written into the very fabric of space-time. When a particle moves through space, it leaves a trace in the quantum field that pervades all of reality. This isn't memory in the conscious sense, but it's information about the particle's history encoded in the structure of the universe itself. Consider the phenomenon of quantum entanglement. When two particles become entangled, they share a quantum state that persists even when they're separated by vast distances. If you measure the spin of one particle, you instantly know the spin of its entangled partner, no matter how far away it is. In a sense, each particle remembers its connection to the other. This quantum memory isn't stored in the particles themselves, it's encoded in the relationships between them. It's as if the universe maintains a vast web of connections, a kind of cosmic memory bank that keeps track of every quantum interaction that has ever occurred. But here's where it gets really strange. This quantum memory seems to be reversible. In principle, if you could track every quantum interaction in the universe and reverse them all simultaneously, you could run the universe backward, undoing every event that has ever occurred. The information would still be there, just organized differently. This suggests that causality, the relationship between cause and effect, might be more complex than we usually think. In the quantum realm, cause and effect can become entangled, with future events influencing past ones in subtle ways. Some interpretations of quantum mechanics suggest that particles can even remember future measurements, adjusting their behavior in the present to be consistent with what will happen later. This creates a fascinating picture of temporal causality. Instead of a simple chain of cause and effect stretching from past to future, we might have a complex web of relationships that extends in all directions through time. Particles don't just carry information about their past, they might be influenced by their future as well. The implications are profound. If particles can remember and if that memory is reversible, then in principle, every event that has ever occurred is still encoded somewhere in the quantum structure of reality. The universe might be like a vast library, with every moment that has ever existed still stored in the quantum information that flows through space-time. This raises deep questions about the nature of time and memory. Are your memories fundamentally different from a particle's memory, or are they both aspects of the same underlying phenomenon? The universe's way of maintaining information about its own history. Imagine that all of time, past, present, and future, exists simultaneously, like a vast four-dimensional sculpture that contains every moment that has ever been or ever will be. This is the block universe, and it's one of the most mind-bending implications of Einstein's relativity. In this view, your birth, your childhood, this very moment, and your future are all equally real. They exist as fixed points in the four-dimensional structure of space-time, like cities on a map. The feeling that time flows, that the present moment is special, that the past is gone and the future is yet to come. All of this might be an illusion created by the way consciousness navigates through the temporal landscape. Think of it like watching a movie. The entire film exists on the reel. Beginning, middle, and end are all there simultaneously, but you can only experience it one frame at a time, creating the illusion of motion and narrative flow. Similarly, your entire life might exist simultaneously in the block universe, but you can only experience it one moment at a time. This raises profound questions about the nature of existence and identity. If all moments exist simultaneously, then in what sense are you the same person who was born decades ago? Are you a single, continuous entity moving through time? Or are you a collection of time slices, each existing at a different moment in the block universe? The block universe also challenges our intuitions about causality and free will. If the future already exists, is it already determined? When you make a choice, are you creating the future, or are you simply playing out a script that's already been written in the four-dimensional structure of spacetime? Some physicists and philosophers argue that the block universe is the most natural interpretation of relativity. Since simultaneity is relative, events that are simultaneous for you might not be simultaneous for someone else. There's no universal now that divides past from future. Instead, all events exist in a timeless, four-dimensional reality. But this view comes with its own puzzles. If all moments exist simultaneously, why do we experience time as flowing? Why do we remember the past but not the future? Why does causality seem to run from past to future rather than the other way round? One answer involves the concept of entropy. Even in a block universe, there's an asymmetry between past and future created by the second law of thermodynamics. The past is the direction of lower entropy. The future is the direction of higher entropy. This might be what creates the arrow of time, not the flow of time itself, but the direction in which entropy increases. Another answer involves consciousness itself. Perhaps consciousness is what creates the experience of temporal flow by selecting which slice of the block universe to pay attention to. In this view, time doesn't flow. Instead, consciousness moves through time, creating the illusion of temporal passage. The block universe might seem cold and deterministic, but it also contains something beautiful, the idea that everything that has ever mattered still exists. Every moment of joy, every act of love, every achievement and discovery, all of it is preserved in the eternal structure of space-time. Nothing is truly lost. It's all still there, waiting to be experienced again by consciousness as it moves through the temporal landscape. Let's venture into the realm of time travel, not just the science fiction kind, but the real physics of closed time-like curves, wormholes, and the strange possibilities that emerge when space-time folds back on itself. Einstein's general relativity doesn't prohibit time travel. In fact, it predicts several ways that time travel might be possible. Rotating black holes, known as Kerr black holes, could theoretically contain closed time-like curves paths through space-time that loop back to their own past. Wormholes, hypothetical tunnels through space-time, might allow shortcuts not just through space but through time as well. But time travel creates paradoxes that challenge our understanding of causality and consistency. The most famous is the grandfather paradox. If you travel back in time and prevent your grandparents from meeting, how could you have been born to travel back in the first place? It's a logical contradiction that seems to tear at the fabric of reality itself. One solution to the grandfather paradox is the many worlds interpretation of quantum mechanics. In this view, traveling back in time doesn't change your original timeline, it creates a new one. When you prevent your grandparents from meeting, you split the universe into two branches. One where they never met, and you were never born, and another where they did meet, and you continue to exist. You can travel between these branches, but you can't create logical contradiction. Another solution involves the Novikov self-consistency principle, named after physicist Igor Novikov. This principle suggests that the universe somehow prevents paradoxes from occurring. If you try to change the past, something will always intervene to ensure that events unfold exactly as they did before. It's as if the universe has built-in protection against temporal contradiction. But perhaps the most intriguing solution involves the idea that time travel might be possible, but limited. Some physicists propose that you can only travel back to the point when a time machine was first created. Before that point, the necessary closed time-like curves don't exist. It's like having a telephone. You can only call someone if they also have a phone. The physics of time travel also depends on the nature of space-time itself. If space and time are discrete rather than continuous, if they're made up of tiny indivisible units, then time travel might be impossible simply because there's no smooth path back to the past. The universe might be like a digital clock rather than an analog one, with discrete ticks that prevent backward motion. Even if time travel is possible, it might require exotic matter with negative energy density, cosmic strings with enormous tension, or other forms of matter and energy that may not exist in our universe. The energy requirements for creating traversable wormholes or closed time-like curves might be so enormous that they're practically impossible to achieve. But here's what's beautiful about the physics of time travel. It forces us to confront the deepest questions about the nature of time, causality, and reality itself. Even if time travel remains forever beyond our reach, the mere possibility reveals something profound about the structure of space-time and the strange flexibility of temporal relationships. Your body is a time machine, carrying within it ancient rhythms that connect you to the deep cycles of the cosmos. Even as you sleep, biological clocks are ticking away, orchestrating the complex symphony of processes that keep you alive and aware. The most famous of these is your circadian rhythm, the roughly 24-hour cycle that regulates your sleep-wake patterns, body temperature, hormone production, and countless other physiological processes. This internal clock is so precise that it can maintain its rhythm even in the absence of external time cues, like a biological chronometer that keeps ticking in the dark. But your circadian rhythm is just one of many temporal cycles that govern your existence. You have ultradian rhythms that cycle every few hours, controlling things like REM sleep stages and hormone pulses. You have infradian rhythms that unfold over days, weeks, or months, like the menstrual cycle or seasonal changes in mood and metabolism. These biological rhythms aren't just mechanical processes, they're deeply connected to your psychological experience of time. When your circadian rhythm is disrupted by jet lag or shift work, it's not just your sleep that's affected. Your mood, cognitive function, and even your perception of time itself can be altered. During REM sleep, your brain creates dreams that can seem to last for hours, but occur in minutes. Time becomes fluid, elastic, shaped by the strange logic of the unconscious mind. You might dream of entire conversations, epic adventures, or complex problem-solving scenarios, all compressed into brief bursts of neural activity. This suggests that time perception is more flexible than we usually realize. Your brain doesn't just passively measure time. It actively constructs temporal experience from multiple sources of information. The steady tick of your circadian clock, the rhythmic firing of neurons, the flow of memories and associations, all of these contribute to your sense of temporal flow. Indigenous cultures around the world have recognized this connection between biological and cosmic time. The Aboriginal Australian concept of dream time describes a timeless realm where past, present and future coexist, where the stories of creation continue to unfold in the eternal now. This isn't just mythology. It's a sophisticated understanding of the relationship between consciousness and time. Your biological clocks also connect you to the broader rhythms of the natural world. The circadian rhythm evolved to match the 24-hour rotation of the Earth, synchronizing your internal processes with the cycle of day and night. Seasonal rhythms align with the Earth's orbit around the Sun, preparing your body for the changing demands of different times of year. But modern life often disrupts these ancient connections. Artificial light confuses your circadian rhythm, making it harder to maintain healthy sleep patterns. Constant travel across time zones forces your internal clocks to constantly readjust. The 24/7 nature of modern society conflicts with the natural rhythms that have governed life for millions of years. Perhaps the most profound aspect of biological time is its subjectivity. Your internal clocks don't just keep time, they create your personal relationship with time. The way you experience duration, the rhythm of your thoughts and emotions, the pace of your daily life, all of these are shaped by the biological timekeepers that evolved to help your ancestors survive in a world of natural cycles. There are places in the universe where time itself becomes undefined, where the familiar flow of moments breaks down into something unrecognizable. These are the frontiers of physics, where our understanding of time reaches its limits and strange new possibilities emerge. At the center of every black hole lies a singularity, the point where matter is compressed to infinite density and the curvature of space-time becomes infinite. Here the equations of general relativity break down, and with them, our ability to describe what happens to time. It's not that time stops, it's that the very concept of time becomes meaningless. Imagine falling toward a black hole's singularity. As you approach, tidal forces stretch your body, but something even stranger happens to time. The gravitational field becomes so strong that it creates extreme time dilation, but in a way that's impossible to describe with our current physics. Time doesn't just slow down, it becomes fractured, discontinuous, perhaps even multidimensional. The Big Bang presents a similar challenge. At the very beginning of the universe, all of space and time emerged from a singularity. But what does it mean for time to have a beginning? What existed before the first moment? These questions push language and mathematics to their breaking points. Some physicists propose that time might be discrete, rather than continuous, made up of tiny, indivisible units called chronons. If this is true, then at the smallest scales time wouldn't flow smoothly, but would tick from moment to moment like a cosmic digital clock. The Planck time, about 1043 seconds, might represent the smallest possible interval of time, the fundamental tick of the universe's temporal machinery. At these scales, the distinction between space and time might disappear entirely. Quantum gravity theories suggest that space-time itself might be emergent, arising from more fundamental quantum processes. Time might not be a dimension at all, but rather a property that emerges when quantum systems interact and create the illusion of temporal flow. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that our familiar notions of time break down at the smallest scales. Some theories propose that time has multiple dimensions, others suggest that it's quantized into discrete units, and still others argue that it's not fundamental at all, but emerges from timeless quantum processes. The breakdown of time also occurs in certain cosmological scenarios. If the universe undergoes eternal inflation, creating an infinite number of bubble universes, then the notion of cosmic time becomes problematic. Different regions of the multiverse might have different temporal structures, different rates of time flow, even different numbers of time dimensions. Perhaps most intriguingly, some physicists propose that time might be reversible under certain extreme conditions. In the quantum realm, time reversal symmetry suggests that the fundamental laws of physics work equally well in both directions. If this symmetry is exact, then there might be processes that can literally reverse the flow of time, undoing past events and creating backward causality. These breakdowns of time don't necessarily mean that time doesn't exist. They might mean that time is more complex and multifaceted than we currently understand. Just as the discovery of quantum mechanics revealed that matter and energy behave differently at small scales, the breakdown of time at extreme scales might reveal new aspects of temporal reality. Look up at the night sky, and you're seeing the universe's autobiography written in light. Every star, every galaxy, every distant quasar carries information about cosmic time, not just when it existed, but how the universe itself has aged and evolved over billions of years. The universe is currently about 13.8 billion years old, an age we can measure by observing the cosmic microwave background radiation that fills all of space. This radiation is the afterglow of the Big Bang, stretched and cooled by the expansion of space itself. It's like cosmic baby pictures, showing us what the universe looked like when it was only 80,000 years old. But aging implies change, and change implies time. The universe has evolved from a hot, dense state to the cooler, more spread-out cosmos we see today. Stars have formed and died, galaxies have collided and merged, and the overall entropy of the universe has increased. This evolution suggests that the universe experiences time in a meaningful way. Yet this raises profound questions. If the universe is everything that exists, what does it mean for it to age? Aging usually implies change, relative to some external reference frame, but there's nothing external to the universe. The universe contains all of space and time. It doesn't exist within time. Time exists within it. One way to think about cosmic aging is in terms of entropy. The second law of thermodynamics tells us that entropy in a closed system always increases over time. The universe started in a state of extremely low entropy, highly organized with tremendous potential for change. Since then, entropy has been increasing, driving the formation of stars, galaxies, and eventually complex structures like planets and life. This increase in entropy might be what creates the arrow of time on a cosmic scale. The universe ages, not because it moves through time, but because it evolves from states of lower entropy to states of higher entropy. The direction of cosmic time is the direction in which entropy increases. But entropy increase also predicts a grim future for the universe. As the cosmos continues to expand and cool, stars will eventually exhaust their fuel and die. Black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, known as heat death. In this far future, there will be no more sources of free energy, no more complexity, no more change. Does this mean that time itself will end? Or does it mean that time will continue forever, even in a universe that has reached maximum entropy? These questions touch on the deepest mysteries of cosmology and thermodynamics. Some physicists propose that the universe might be cyclic, going through endless cycles of expansion and contraction, birth and death. In this view, our current universe might be just one phase in an eternal cycle, with time extending infinitely in both directions. The Big Bang wouldn't be the beginning of time, but just the beginning of our current cosmic cycle. Others suggest that the universe might spawn baby universes through quantum processes, creating a multiverse where different regions have different temporal structures. Time might be local, rather than universal, with each pocket universe having its own temporal evolution. The aging of the universe also connects to the deep puzzle of why time has a direction. In a universe that started with low entropy and is evolving toward higher entropy, the past and future are fundamentally different. The past is the direction of organization, the future is the direction of randomness. This asymmetry might be what creates our experience of temporal flow. What if time isn't fundamental to reality, but emerges from something deeper? This is one of the most revolutionary ideas in modern physics, suggesting that time might be like temperature or pressure, a macroscopic property that arises from the collective behavior of more basic components. The idea of emergent time comes from several different areas of physics. In quantum mechanics, the fundamental equations are time reversible, yet we experience time as flowing in one direction. In thermodynamics, the arrow of time emerges from the statistical behavior of countless particles. In general relativity, time and space are unified into space-time, but the special role of time remains mysterious. Some physicists propose that time might emerge from quantum entanglement. In this view, the universe is fundamentally made of quantum information, with particles and forces arising from patterns of entanglement between basic units of information. Time might be the way these patterns evolve and change, creating the illusion of temporal flow. The holographic principle, inspired by studies of black hole physics, suggests that all the information in a volume of space can be encoded on its boundary. This principle implies that the three-dimensional world we experience might be a projection of information stored on a two-dimensional surface. If this is true, then time might also be emergent, a way of organizing information rather than a fundamental dimension. String theory offers another perspective on emergent time. In string theory, the fundamental objects are not particles, but tiny vibrating strings. The properties of particles, their mass, charge, and other characteristics, emerge from the vibrational patterns of these strings. Time might be similar, emerging from the way strings vibrate and interact in higher dimensional space. Loop quantum gravity takes a different approach, proposing that space and time are quantized at the smallest scales. In this theory, space-time is made of discrete units, like pixels on a computer screen. Time emerges when these units interact and create the appearance of continuous flow. It's like watching a movie. The film is made of discrete frames, but the rapid succession of frames creates the illusion of smooth motion. The idea of emergent time also appears in cosmology. Some theories propose that time began with the Big Bang, emerging from a timeless quantum state. Before the Big Bang, there was no time, no space, no causality, just pure quantum potential. The universe's evolution from this timeless state to the time-bound cosmos we observe might be the ultimate example of time emergence. But emergence raises its own puzzles. If time emerges from something more fundamental, what ensures that it emerges in the same way everywhere? Why do we all experience time flowing in the same direction? Why does emergent time seem so smooth and continuous, when its underlying substrate might be discrete and discontinuous? Perhaps the answer lies in the nature of consciousness itself. If time is emergent, then perhaps consciousness is what allows us to experience that emergence. Your brain might be like a time detection device, evolved to sense and respond to the temporal patterns that emerge from quantum processes. Time might not exist without consciousness to perceive it. This leads to a beautiful paradox. If time is emergent and consciousness is required to experience it, then time might be both objective and subjective simultaneously. It emerges from physical processes that exist independently of consciousness, but it only becomes meaningful when consciousness is there to experience it. Here's something beautiful to consider as we continue our journey. Every culture that has ever existed has had to make peace with time in its own unique way. Like artists with the same canvas, human societies have painted time in colors that would amaze and perplex each other. The ancient Greeks gave us two words for time that still whisper wisdom today. Chronos, the mechanical, measurable time of clocks and calendars, the time that ages our bodies and governs our schedules. But then there's Kairos, the perfect moment, the right time, the instant when everything aligns just so. It's the difference between the time it takes to fall in love and the moment you realize you already have. In the villages of Madagascar, the Malagasy people speak of time as if it flows backward. The past is in front of them, visible, known, like a path they can see. The future lies behind them, invisible and unknowable, like the back of their heads. When they discuss events, they literally face the past and turn their backs to the future. What would our anxiety about tomorrow feel like if we couldn't see it coming? The Hopi people of the American Southwest have created a language that barely acknowledges time as we understand it. They don't conjugate verbs into past, present, and future tenses. Instead, they speak of events as either manifest, visible, evidential, or unmanifest, still forming, potential. A Hopi speaker might describe a sunset not as the sun will set, but as the sun is setting, capturing the eternal, ongoing nature of the process, rather than fixing it in time. Aboriginal Australians carry perhaps the most profound relationship with time in their concept of the dream time. This isn't a period that happened long ago, but an eternal present where all stories, all creation, all existence exist simultaneously. The dream time is not past, it's accessible now, threaded through every moment and every place. Time becomes not a river but an ocean where ancestors, spirits, and future generations all swim together. Buddhist philosophy offers us the concept of the eternal now, where past and future are seen as mental constructs that pull us away from the only moment that truly exists. Yet paradoxically, Buddhism also teaches about countless lifetimes stretching across eons, creating a relationship with time that is both immediate and vast beyond imagination. In medieval Europe, time was understood through bells, monastery bells that divided the day into prayers, church bells that called communities together. Time was communal, sacred, circular rather than linear. The idea that time could be private, vernal, something you could save or waste, was almost incomprehensible. People lived in time rather than trying to manage it. The Industrial Revolution changed everything. Suddenly, time became money, something to be spent, saved, invested, or lost. Factory whistles replaced church bells. Time became a commodity to be bought and sold. We began to speak of spending time as if it were coins in our pockets, and saving time as if it were grain in our barns. Japanese culture gives us the concept of mono no aware, the bittersweet awareness of the impermanence of all things. It's the feeling you get watching cherry blossoms fall, knowing their beauty lies partly in their brevity. Time isn't just a measurement, but an aesthetic experience, a way of finding beauty in transience itself. Modern digital culture has created its own temporal language. We speak of real time, lag time, downtime. We've created a world where milliseconds matter, where delays of heartbeats can mean the difference between connection and isolation. We've made time more precise than ever before, yet somehow it feels more elusive. Indigenous cultures around the world often speak of cyclical time seasons, generations, the great wheel of existence turning eternally. Linear time, with its emphasis on progress and future goals, can seem like a kind of madness from this perspective. Why rush toward a future when you're already part of an eternal cycle? What emerges from this beautiful tapestry of cultural time is a stunning realization. Time might not be something we discover, but something we create. Each culture doesn't just measure time differently. They actually experience different kinds of time. The ticking clock on your wall isn't just marking universal moments. It's speaking one particular language of time among thousands of possible languages, and perhaps that's the deepest wisdom here. If time is so malleable, so shaped by consciousness and culture, then asking whether it exists might be like asking whether language exists. It's real because we make it real, and it's different because we make it different. Let's drift now into the strangest library in existence, the realm of mathematics, where time seems to have forgotten how to tick. Here, in the elegant world of equations and theorems, we find something peculiar. The fundamental laws that govern our universe appear to be frozen in eternal stillness. Picture yourself standing before Newton's law of universal gravitation, written in its pristine mathematical form. Phi, Vg, m1, m2, r, tau. This equation doesn't age, doesn't change, doesn't evolve. It doesn't care if you're reading it in 1687 or 2087. It exists in a realm beyond time, as eternal and unchanging as a perfect crystal. This timeless quality of mathematics creates a beautiful paradox. The equations that describe motion, change, and temporal flow are themselves utterly static. It's like discovering that the score for a symphony, with all its rushing crescendos and gentle diminuendos, is written in unchanging ink on paper that never ages. Einstein's field equations of general relativity reveal this mystery even more deeply. When physicists write E a mech c quo, they're not describing something that happens in time. They're describing a relationship that exists outside of time entirely. Energy and mass are connected by this eternal mathematical truth. Whether the universe is 1 second old or 15 billion years old, consider the exquisite symmetries that mathematics reveals in nature. A snowflake's six-fold symmetry, the spiral of a nautilus shell, the geometric patterns in flower petals. These aren't accidents of timing, but expressions of timeless mathematical principles. The golden ratio that spirals through sunflowers and galaxies alike isn't something that developed over time. It's a mathematical constant that was true before the first star formed and will remain true after the last star dies. In the mathematical world, the concept of before and after becomes almost meaningless. Pythagoras' theorem isn't waiting to be discovered. It exists in eternal perfection, independent of whether any mind has grasped it yet. The prime numbers march on in their infinite sequence, not because time is pushing them forward, but because mathematical truth requires no temporal unfolding. This leads us to a profound question. If the fundamental laws of physics are mathematical, and mathematics exists outside of time, then what does this say about the nature of physical reality itself? Perhaps the universe isn't really evolving through time, but rather expressing different aspects of a timeless mathematical structure. The physicist Max Tegmark has proposed that our universe might literally be a mathematical object, not described by mathematics but actually made of mathematics. In this view, what we experience as time might be like reading through the pages of a book. The entire book exists at once, complete and unchanging, but our consciousness moves through it sequentially, creating the illusion of temporal flow. Quantum mechanics adds another layer to this mystery. The Schrödinger equation, which governs the behavior of quantum particles, is what mathematicians call time reversible. Run it forward or backward, and it works equally well. At the quantum level, the fundamental laws of physics show no preference for past or future. Time's arrow, so obvious in our everyday experience, seems to vanish in the mathematical foundations of reality. Group theory, one of mathematics' most beautiful creations, reveals that the deepest symmetries in nature are those that remain unchanged under transformations of time. The perfect circle looks the same whether you rotate it, reflect it, or in the mathematical realm translate it through time. The universe's most fundamental symmetries exist in a space where time has no meaning. Even more intriguingly, some of the most successful theories in physics suggest that space and time might emerge from more fundamental timeless mathematical structures. String theory proposes that the deepest level of reality consists of vibrating mathematical objects in dimensions beyond our perception. Loop quantum gravity suggests that space and time themselves might be woven from discrete, timeless mathematical entities. Consider the beautiful mathematics of fractals, geometric patterns that repeat at every scale, from the smallest zoom to the largest. A fractal doesn't develop over time, it simply is, existing in its full complexity at every moment. Some physicists wonder if the universe itself might be fractal-like, with its apparent temporal development being simply different scales of the same timeless mathematical pattern. What's particularly fascinating is that when mathematicians study chaos theory, the mathematics of complex, seemingly random systems, they find that even chaos follows timeless mathematical laws. The butterfly effect, the strange attractors, the sensitive dependence on initial conditions, all of these temporal phenomena emerge from equations that themselves exist outside of time. Perhaps the most profound insight from mathematics is that time might be what mathematicians call an emergent property, something that appears to exist at one level, but dissolves when you look more deeply. Just as the wetness of water emerges from H2O molecules that aren't themselves wet, time might emerge from timeless mathematical relationships that aren't themselves temporal. This mathematical perspective suggests that asking whether time exists is like asking whether the number 7 exists. It's a category error, confusing the map with the territory, the description with the thing described. Time might be real in the same way that mathematics is real, but that reality might be very different from what we imagine. Now let's wander into, perhaps the most modern perspective on time's mystery, the idea that time might not be a flowing river or a ticking clock, but rather something closer to a vast cosmic library of information. This is where physics meets information theory, and where our question about time's existence takes on a distinctly digital flavor. Imagine for a moment that you could zoom into any moment of your life with infinite precision. You'd see not dots where things are, but the exact position and velocity of every atom in your body, every photon bouncing around the room, every quantum state of every particle in your vicinity. This complete snapshot would contain an enormous amount of information, like an ultra-high-resolution photograph of reality itself. Now imagine taking another snapshot a moment later, then another. Each snapshot would be slightly different from the last, like frames in a cosmic movie. The question that's been puzzling physicists is this: is time the movie itself, or is it simply the difference between the frames? This is where the concept of entropy enters our gentle exploration. Entropy is often described as disorder, but it's more accurately understood as information. When you shuffle a deck of cards, you're not creating chaos, you're creating a unique arrangement that contains information about the shuffling process. The universe might be similar, constantly shuffling itself into new configurations, and what we call time might be simply the accumulation of these informational changes. Think about your own memories for a moment. They're not stored as little movies in your brain, but as patterns of neural connections, information encoded in the physical structure of your mind. Your sense of time passing might be nothing more than your brain's way of organizing and accessing this informational library. The past exists as information patterns, the present is the active processing of new information, and the future is the space of possible information configurations. Computer scientists have discovered something remarkable. Any computation, no matter how complex, can be understood as a process of transforming information. Your smartphone isn't really doing anything in the traditional sense. It's simply moving bits of information around according to precise rules. What if the universe is similar? What if what we call time is simply the universe computing itself, processing information from one state to the next? This perspective suggests that time might be less like a river and more like a computer program running. Each moment would be like a single computational step, where the universe takes its current informational state and transforms it according to the laws of physics. The flow of time wouldn't be something external to reality, but rather the very process by which reality updates itself. The physicist John Wheeler captured this beautifully in his phrase, "it from bit." The idea that everything in the universe, including time itself, might emerge from pure information. In this view, matter and energy aren't the fundamental building blocks of reality. Information is. Time becomes the universe's way of processing and organizing this information. Quantum mechanics adds a fascinating twist to this story. At the quantum level, information can exist in superposition, multiple states, simultaneously. Before a quantum measurement, a particle doesn't have a definite position or velocity. It exists in a cloud of informational possibilities. The act of measurement doesn't reveal pre-existing information. It actually creates information by forcing the quantum system to choose one possibility from many. This suggests that time might be fundamentally connected to the creation of information. Each moment might be the universe making countless quantum measurements, constantly creating new information, and collapsing possibilities into actualities. Time's arrow might point not toward the future, but toward increasing information content. The concept of entropy provides another clue. The second law of thermodynamics tells us that entropy, informational complexity, always increases over time. But here's the intriguing part. This law might not be describing time so much as defining it. Perhaps time's direction emerges from the universe's tendency to explore new informational states. Like a cosmic explorer always venturing into unexplored territory. Consider the information in a melting ice cube. Initially, the water molecules are arranged in a highly ordered crystal structure, low entropy, low information content. As the ice melts, the molecules move into countless possible positions. High entropy, high information content. The direction we call time might be nothing more than the direction of increasing informational complexity. This perspective offers a beautiful answer to the question of whether time exists without change. If time is information, then a perfectly static universe would be like a computer that never updates, informationally frozen. Time would still exist as potential, like a paused video that could resume at any moment, but it wouldn't be active, wouldn't be flowing. The implications are profound. If time is information, then the past isn't gone. It's simply encoded in the present state of the universe. Every atom in your body carries informational traces of its history, like a library book that remembers every reader who has touched its pages. The future isn't somewhere we're heading. It's a space of possible informational configurations that the universe is constantly exploring. This informational view of time also suggests why consciousness and time seem so intimately connected. Consciousness might be the universe's way of processing information about itself. Our sense of time's passage might be the subjective experience of information processing, the feeling of reality computing itself moment by moment. In this gentle perspective, time becomes less mysterious and more intimate. It's not some external force pushing us forward, but rather the very process by which the universe and we as part of it continuously creates itself through the dance of information and possibility. Let's settle into perhaps the most intimate question about time's nature. Imagine a universe where absolutely nothing happens. No particles moving, no energy flowing, no thoughts thinking, no hearts beating. A cosmos frozen in perfect stillness, like a photograph that never fades. In such a universe, would time still exist, flowing invisibly through the eternal stillness? This question has puzzled philosophers and physicists for centuries, and it cuts to the very heart of what we mean when we ask whether time exists. Because if time can exist without change, then it must be something fundamental, the stage upon which the universe performs, rather than the performance itself. Picture yourself sitting in a perfectly quiet room, so still that you can hear your own heartbeat. Now imagine even that heartbeat stopping, your thoughts pausing mid-sentence, every molecule in your body frozen in place. Would time still be passing around you, or would it pause too, waiting patiently for movement to resume? The ancient philosopher, Aristotle, wrestled with this question, and concluded that time and change are so intertwined that one cannot exist without the other. In his gentle wisdom he suggested that time is the measure of change, not a thing in itself, but rather the way we quantify and understand transformation. Without change, Aristotle argued, time would be as meaningless as trying to measure the length of something that doesn't exist. But Newton, centuries later, envisioned something quite different. He imagined time as a vast invisible river, flowing steadily regardless of what happens within it. In Newton's universe, time flows at the same rate whether planets are spinning or sitting still, whether stars are being born or dying quietly in the darkness. Time in this view is absolute and independent, cosmic clockwork that ticks on regardless of the universe's activities. Einstein's relativity changed everything, suggesting that time and space are woven together into a single fabric. But even Einstein's space-time raises our question. If you could somehow remove all matter and energy from the universe, would empty space-time still exist? Would time still flow through that cosmic void? Consider the strange case of a photon traveling through space. From the photon's perspective, if we can imagine such a thing, time doesn't pass at all. The moment it's created, and the moment it's absorbed, happens simultaneously in its reference frame. Yet, from our perspective, we see the photon traveling, taking time to cross the vast distances between stars, which perspective reveals the truth about time's existence. Modern physics offers some tantalizing clues. In quantum mechanics, even empty space isn't truly empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence like cosmic butterflies. These fluctuations might be the universe's way of ensuring that perfect stillness is impossible. Perhaps time requires these quantum changes to exist, like a river that needs at least some flow to remain a river. The concept of entropy provides another perspective. Entropy, as we explored earlier, is intimately connected to information and change. In a perfectly static universe, entropy would be constant, neither increasing nor decreasing, but the second law of thermodynamics tells us that entropy always increases over time. This creates a beautiful paradox. If time requires entropy to increase, then perfect stillness might indeed stop time itself. Some physicists have proposed that time might be an emergent property, something that appears when you have enough complexity and change, but disappears when things become too simple, like how consciousness emerges from neural complexity, but vanishes under anesthesia. Time might emerge from cosmic complexity, but fade away in perfect simplicity. There's a beautiful thought experiment that illuminates this mystery. Imagine a universe containing only two particles, perfectly still, separated by some distance. Now imagine that one particle suddenly moves slightly toward the other. At that moment, would time begin? Would the universe suddenly acquire a past, when the particle was farther away, and a future, when it might be closer? Or would time have been flowing all along, waiting for something to mark its passage? The Buddhist concept of emptiness offers another perspective. In Buddhist philosophy, emptiness doesn't mean nothingness. It means the absence of independent existence. Perhaps time, like all phenomena, has no independent existence, but arises in dependence upon change, consciousness, and the web of relationships that constitute reality. Consider your own experience of time during deep dreamless sleep. From your perspective, time seems to disappear. You close your eyes and suddenly it's morning, with no subjective experience of the hours between. Yet clocks continue ticking, the earth continues spinning, change continues happening around your still form. Does time exist during your subjective absence from it? Some philosophers argue that time without change is like music without sound, a category error that confuses the abstract measurement with the concrete phenomenon. Others suggest that time might be like a stage that exists whether or not actors are performing upon it. The most profound insight might be that this question reveals the fundamental mystery of time itself. If time can exist without change, then it's something more fundamental than we imagined. If it can't, then time is more intimate and dependent than we thought, less like a cosmic backdrop, and more like a relationship between things, a way that reality has of being with itself. Perhaps the answer is that time and change are like two sides of the same coin, so intimately connected that separating them is like trying to separate wetness from water. In the deepest sense, asking whether time exists without change might be like asking whether dancing exists without dancers, or whether love exists without lovers. As we drift toward the end of our gentle journey, let's allow our minds to wander into the vast future, not just tomorrow or next year, but to the very edge of time itself. What happens when the universe grows old? What lies beyond the last tick of the cosmic clock? And in that ultimate stillness, what might we discover about the nature of time itself? The universe, cosmologists tell us, is expanding and cooling. Stars are burning through their fuel, galaxies are drifting apart, and slowly, very slowly, the cosmos is settling into an ever deeper stillness. This process has a name that sounds almost poetic: heat death. But don't let the name frighten you. It's not a violent end, but rather the universe's gentle drift toward a state of perfect equilibrium. Imagine the universe as a vast cup of tea, slowly cooling toward room temperature. Eventually, after trillions upon trillions of years, the last star will flicker out, the last black hole will evaporate through Hawking radiation, and the universe will settle into a state of maximum entropy, a perfect, unchanging stillness, where no energy flows, because all energy has been evenly distributed. In this final state, would time still exist? It's a question that would have delighted the ancient philosophers, and continues to puzzle modern physicists. If time requires change to exist, then the heat death of the universe might also be the death of time itself. The cosmic clock would wind down not with a bang, but with the gentlest of whispers, finally falling silent. But here's where the story becomes beautifully strange. Some physicists speculate that even in this ultimate stillness, quantum fluctuations would continue, tiny, random variations in the quantum vacuum that might occasionally, after incomprehensibly long periods, spontaneously create new structures. Perhaps time wouldn't end, but would transform, becoming something more patient and subtle than we can imagine. Consider the concept of Poincare recurrence, the idea that any finite system will eventually return to its initial state. If the universe is finite, then given enough time, far more time than we can meaningfully contemplate, every possible configuration of matter and energy will eventually reoccur. Your exact pattern of thoughts, the precise arrangement of stars, the specific sequence of events that led to this moment, all of it might happen again, infinite times in an eternal cosmic cycle. This leads to a profound question. If time is cyclical rather than linear, then what does after time even mean? Perhaps time doesn't have an end, but rather an eternal return, like a cosmic breath that inhales and exhales forever. In this view, we're not heading toward the end of time, but toward its endless renewal. Some theories in physics suggest even more radical possibilities. The multiverse hypothesis proposes that our universe is just one bubble in an infinite foam of universes, each with its own version of time. The heat death of our universe might be like a single note ending in an infinite symphony, with countless other melodies continuing to play in parallel realities. Loop quantum gravity suggests that time itself might be quantized, made of discrete, indivisible moments like frames in a cosmic movie. In this view, time might not end, but might become increasingly sparse with longer and longer gaps between moments until the universe experiences time as a series of isolated instants, separated by eternities of stillness. String theory opens up even more exotic possibilities. In some versions, time is just one dimension among many, and what we experience as temporal flow might be our limited perception of movement through higher dimensional space. The end of time in our universe might be like reaching the edge of a country, not the end of existence, but simply the boundary of our particular domain. There's a beautiful contemplation in imagining consciousness in such a far future. If conscious beings somehow survived the heat death of the universe, perhaps as patterns of information rather than biological entities, how would they experience time? Would they remember the era of stars and planets as a brief, brilliant flash? Would they develop new forms of temporal awareness, suited to their timeless environment? The concept of eternal inflation suggests that while our local universe might be winding down, the larger cosmos might be constantly creating new regions of space-time. In this view, time doesn't end, but rather splits into countless branches, each beginning its own temporal journey. The end of time in our universe would be like a river reaching the ocean, not disappearing but joining something vast and eternal. Some philosophers and physicists have proposed that time might be fundamentally cyclical, with the universe periodically returning to its beginning state. The Big Bang might not be the start of time, but rather the latest iteration in an endless cycle of cosmic expansion and contraction. In this view, asking what happens after time is like asking what happens after today, tomorrow, in one form or another. It always comes. Perhaps the most profound speculation is that the end of time might reveal time's true nature. If time is indeed an emergent property of complexity, then its gradual disappearance might show us what lies beneath, some more fundamental aspect of reality that doesn't require temporal flow to exist. The heat death of the universe might not be an ending, but a transformation, like a butterfly emerging from its chrysalis. What we call time might be just one phase in the universe's development, and beyond it might lie forms of existence so different from our current experience that our temporal language can't even describe them. In the end, contemplating what happens after time might be the most human response to the mystery of time itself. We're beings who exist in time, and so we naturally wonder about time's boundaries. Perhaps the question itself is the answer, that the capacity to ask about time's end is itself a form of transcendence, a way of reaching beyond our temporal limitations through the power of imagination and wonder. And so we return, like gentle travelers completing a circle, to the question that began our journey. Does time even exist? Or is it all in our minds? After wandering through multiverse clocks and cultural time languages, through timeless mathematics and informational flows, through changeless eternities and post-temporal futures, we find ourselves back where we started, but perhaps with eyes that see a little differently. Imagine, one final time, stepping completely outside the universe as we know it. You're in a place where there are no clocks, no calendars, no beating hearts or spinning planets. From this impossible vantage point, you can see the entire history of the cosmos, laid out like a vast four-dimensional sculpture: the Big Bang, the formation of stars, the evolution of life. This very moment, as you read these words, the distant future heat death of the universe, all of it exists simultaneously, eternally, timelessly. In this view, time doesn't flow like a river. It simply is like a mountain or a crystal. What we experience as temporal flow might be nothing more than the path our consciousness takes through this eternal structure. Like a reader moving through the pages of a book, the book exists complete and whole, but we experience it sequentially, creating the illusion of a story unfolding in time. This is the block universe theory, and it suggests that time might be the universe's most beautiful illusion. Every moment you've ever experienced, your first laugh, your deepest sorrows, your quiet moments of wonder, still exists, frozen in the eternal crystal of space-time. Nothing is ever truly lost, because in the deepest sense, everything is always there. But here's the profound mystery. If time is indeed an illusion, it's an illusion that creates itself. Our brains, evolved over millions of years to navigate a temporal world, create the very experience of time that we're questioning. The neuronal processes that generate our sense of temporal flow are themselves embedded in the supposedly timeless structure of the universe. This creates a beautiful paradox. If time is all in our minds, then our minds, which are part of the universe, are somehow dreaming time into existence. The universe might be using conscious beings like us to experience itself temporally, to know what it's like to have a past and future, to feel the bittersweet passage of moments. Consider the quantum measurement problem once more. At the quantum level, particles exist in superposition, all possible states simultaneously, until they're observed. The act of observation collapses this superposition into a single definite state, but observation requires consciousness, and consciousness requires time. Perhaps consciousness and time are co-creating each other in an endless, circular dance. Some physicists propose that consciousness might be the universe's way of collapsing quantum possibilities into classical realities. If so, then time might be the rhythm of this collapse, the heartbeat of the universe becoming actual rather than merely possible. In this view, Asking whether time exists is like asking whether consciousness exists. They're so intertwined that one cannot exist without the other. The Buddhist concept of interdependence offers another way to think about this. Nothing exists independently. Everything arises in dependence upon conditions. Time might not exist as a thing in itself, but rather as a relationship, a way that the universe has of being with itself, of experiencing its own existence. This perspective suggests that the question, does time exist, might be like asking, does love exist, or does beauty exist? These aren't things you can point to or measure directly, but they're real in the sense that they emerge from the complex interactions of simpler elements. Time might be similar, not a fundamental ingredient of reality, but an emergent property of the universe's complex self-organization. The anthropic principle suggests that we observe the universe having the properties it does, because if it were different, we wouldn't be here to observe it. Perhaps time exists because consciousness exists, and consciousness exists because time exists. The universe might have evolved temporal properties precisely because those properties allow for the emergence of beings who can contemplate time's existence. What's most beautiful about this mystery is that it reveals something profound about the nature of existence itself. Whether time is fundamental or emergent, whether it's real or illusory, whether it flows or simply is, the fact that the universe has given rise to beings who can ask these questions suggests that reality itself is far more mysterious and wonderful than we might have imagined. Perhaps the deepest answer to our question is that time exists in the asking. The very fact that we can contemplate time's nature, that we can wonder about its reality, that we can feel its passage and question its existence, this might be time's most profound manifestation. Time might exist not as a thing, but as a capacity. Not as a substance, but as a relationship, not as a container, but as a dance. In the end, whether time exists might be less important than how we choose to live within the mystery of it. If time is real, then each moment is a gift from the universe itself. If time is an illusion, then we are participating in the cosmos's most beautiful dream. Either way, we find ourselves here now, conscious and wondering, and that might be the most miraculous thing of all. As you settle into sleep tonight, you might carry with you this gentle paradox. Time might be the universe's way of ensuring that everything doesn't happen at once. Or, it might be consciousness's way of experiencing eternity one moment at a time. Perhaps time is both the question and the answer, both the mystery and its own solution. The clock on your wall will continue its patient ticking, measuring moments in the language we've chosen to speak. But now you know that behind that familiar rhythm lies one of existence's deepest puzzles. A mystery so profound that it encompasses everything from the quantum dance of particles to the cultural dreams of civilizations, from the timeless truths of mathematics to the flowing river of consciousness itself. Whether time exists or not, this moment exists. Whether time flows or stands still, you are here, aware, contemplating the very nature of existence, and in that contemplation, perhaps, we find time's deepest truth, that the universe has evolved not just the capacity to exist, but the capacity to wonder about its own existence. Sleep well, knowing that you are part of this cosmic mystery, this beautiful dance between being and becoming, between the eternal and the temporal. Whether time is real or illusory, whether it flows or simply is, you are here now, a conscious part of the universe questioning its own nature, and that, perhaps, is the most timeless truth of all.